We have done research and engineering applications in the past 20 years for this topic. You see, I'll include a basic introduction of China's ground-coupled heat pump application, research and application, and followed by our studies. The study on heat and mass transfer of vertical and inclined borehole ground heat exchangers. The study on hybrid ground-coupled heat pumps, study on solar-aided ground-coupled heat pumps, study a ground-coupled heat pump system with foundation pile ground heat exchangers. You see, for our studies, we study the basic fundamental research about heat and mass transfer for vertical borehole first, and then followed by hybrid and solar-aided, and then foundation pile gradually. This is a general approach from my research group. For ground-coupled heat pump system, it is for air conditioning. We know air conditioning energy consumption accounts for nearly 33% worldwide.
Slides are not changing.
Slide what? Oh, doesn't work?
Yeah.
Eh? That's funny. Wait a minute. Eh? Okay, okay.
Yeah.
Let's use this one. Okay. You see, we mainly concentrate our studies about 4 research projects. The first one, the heat and mass transfer of vertical and inclined boreholes. The study on hybrid system and study on solar-aided ground-coupled heat pump system. Then finally, ground foundation pile ground heat exchange system gradually. So we have been working in this area for nearly 20 years. And if you check our publication record, we have published many journal papers in this area. I must say we were leading the research. Now, you see, followed by this, we are now applying for a big grant called Strategic STG, Strategic Technology Grant, about this topic. I'll show you later. You know, ground coupled heat pump system, or sometimes people call it ground source heat pump system. In fact, it's used for air conditioning. We know air conditioning system accounts for nearly 33% worldwide. But in Hong Kong, about more than 50% for air conditioning, especially in commercial buildings. Air conditioning, not just including cooling, also including heating, air conditioning. We want to condition air to satisfy people's needs indoor. That means we need to adjust the temperature and the humidity and fresh air as well. So we need air conditioning throughout China, near all the countries. You see, in China, for example, northern China, northern even from Hunan, from Shanghai, we need heating. Especially from Beijing, Harbin, without heating, people cannot survive in winter. So heating is very important in this area. In southern part of China, nowadays we have air conditioners. But 30, 40, 50 years ago, not popular. So without cooling, people can survive, but not comfortable. So, but with the development of economy, many ideas, most of the ideas are now using air conditioning. Even, for example, in Shanghai, Hunan, they even didn't use heating in winter before. But now most families are adding heating system, especially split type air conditioners or window type air conditioners. And in Hong Kong, very popular. Every home, nearly every room, even we have air conditioners. Then, how to supply chilled water for air conditioning or cool air for air conditioning? Usually we use compressed we call it compression refrigeration system to use electricity to produce cool air or chilled water. Then we reject energy into the ground, into the air, into the water. But now we can reject energy into the ground. I'll tell you the benefit. So for the ground couple heat pump system, it is widely used. Not widely, but popular in this area, in the black area. That is Shandong, Hebei, Beijing, even Henan. Nowadays Shanghai, but rarely used in Guangdong, in this warm area, or hot summer, warm winter. I'll tell you why. You see, I mentioned that ground couple heat pump projects are mainly built in cold zone, which takes account for nearly 70% cold zone, especially in this Beijing, this hot summer, cold winter area. The reason is that we can get energy balance on the ground. That is, we can inject energy in summer for cooling and then extract energy from ground for heating in winter. Then we have a balance on the ground. Otherwise, we have imbalance. That's a problem. So that's why we say ground couple heat pump system are mainly distributed in the middle and east part of China, whereas the population is larger and relatively richer as well. It's expensive, maybe. You see, early time, Shandong General University, in fact, started research in China about 30 years ago. And they conduct the first system in Jinan. You say they developed the U-turn of ground heat exchange pipelines and did the thermal conductivity test, thermal response test. The location is in Jinan, Shandong province. You say about 25 years ago, to supply hot water for heating, space heating in winter, and cold water for air conditioning in summer. This is a library in Jinan, completed 2001. Then, gradually, more and more ground couple heat pump system was developed. Here I want to tell you why we don't call it ground source heat pump system. Usually, this is also called ground source heat pump system. It's part of ground source heat pump system. But usually, when we take water from ground and use water above the ground, we call it ground source heat pump system. For now, we don't take any physical source from ground. We only take energy from the ground or inject energy to the ground. So we don't call it ground source heat pumps. We call it ground coupled heat pumps, so that we have the difference. That means we only install pipelines on the ground so that there is heat exchange on the ground. Then no water from underground, of course, no injection of water to the ground, so that the environment is not changed. Because long time ago, 40 years ago, ground source heat pump was very popular by taking water from underground. If you drill 100 or 200 meters in Beijing, Tianjin area, you can get 40-degree hot water. And then people use the hot water for heating, but gradually, no water underground. Because it's not easy to inject water into the ground. That's not easy, because the high pressure underground. So scientists found that it's not a good idea to use hot water from underground. We can install pipeline underground to have heat exchange. So this is called ground coupled heat pump system. Then gradually you can see many large projects of ground coupled heat pump system were developed. You see all of this boreholes, then with U-tube pipelines. You see, many boreholes have to be drilled. Usually, the depth is about 100 meters. You see, this one is in Zhejiang province. This one is in Nanjing. You see, what is the disadvantage? We need land. Of course, this land can be covered by grass, or even, I don't think road, but by grass. Another disadvantage is that if something wrong on the ground, for example, blocking or leakage, then we cannot repair it. It should not be used. So that's all the disadvantages. But what are the advantages to use ground coupled heat pump system? Why do we use ground coupled heat pump system? The reason is that, you see, the current practice of air conditioning system, for example, in Hong Kong, we cool the air. How to cool inside the air? We remove energy from inside to the outside by the air conditioning system. Then this removed energy is rejected to the air outside by air cooled, or to the water by water cooled, or seawater by seawater cooled. That means to the outside environment. But in summer, outside the air temperature is very high, so that the energy efficiency we call the COP, coefficient of performance of air conditioning system, is very low. Outside air temperature 35 degrees Celsius, then the COP is lower, even lower than 3. But underground temperature is cold. We can use tunnel, underground tunnel. Then if we go to the tunnel, we feel cold. Why? Because it's not affected by the outdoor air. Then, if we detect the temperature underground, what is temperature? You know, inside. In Hong Kong, usually, not just in Hong Kong, everywhere, the ground temperature, not that deep temperature, let's say below 3 meters below, the temperature is usually the average between daily highest daily summer temperature and the daily winter temperature, the average highest lowest daily temperatures. In Hong Kong, outside temperature in summer is let's say 35. In winter, that's 10. Then 1035, that's 45. Divided by 2, that's about 22 degrees Celsius. Underground temperature about 22 degrees Celsius. In Beijing, for example, outside temperature in summer, let's say 40. Then winter, let's say 10, negative 10. 40, 10, negative 10, that's negative 10, let's say. This is not 30, it's similar like 35. Then negative 10, that's 25, 28. 28 divided by 2, yeah, 14. So in Beijing area, the ground temperature is about 14 degrees Celsius, something like that. Hong Kong, 22 degrees Celsius. Then compared with outside 35 degrees Celsius air temperature is very low. That's why the COP could be higher. So that's why we use ground coupled heat pump system to inject energy into the ground in summer to have higher COP, then extract energy from underground. Then in winter, even in Hong Kong, in Beijing, for example, 14 degrees Celsius, outside winter air temperature could be negative 5, 9. So the COP of heat pump is higher for heating as well. So that's why we use ground coupled heat pump system. Then you can see more and more projects, smaller, bigger. You can say this is a small project in Shandong, Yantai. I must say, ground coupled heat pump system started not in China, started in Western countries like United States and European countries. The reason is that it is very good for houses, small project. We can drill a few boreholes and then we can supply heating in winter, cooling in summer with very low cost. So it is popular in this area for houses, for high-rise buildings. Then we need large land area for boreholes. This is one, for example, in Beijing. But this one is a very large project. It's an Olympic Sports Center in Jinan of Shandong province. You can see for such a large project, how much energy we need to inject into the ground, so that we need all this area for boreholes. And these are the borehole drilling machine. Yes, this is an Olympic Sports Center in Jinan. In recent years, this is a Xiaoshan one-room machine factory. You can see spacing between each borehole is about 3.5 meter. Depth 50 meter. There are about 320 boreholes. It's easy to calculate the total area needed. You see, this is U-tube inside. Down, up, and we can use pump to circulate the water into the ground and take water from the ground. Of course, we need to cut it. Then connect to the condenser or evaporator of air conditioning system. This is a original pipeline. Another project in Longkou Airport. The floor area is 1,000 square meter. Borehole 174, the depth is 100 feet. It depends on the area. In some area like Beijing, if you drill 100 meter, 200 meter, then you get hot water. That's not very good. It depends on the area. In Shandong, it's very ideal. The drilling cost is very cheap because in this area in Shandong, soil, even 100 meter maybe. But we developed this for research project, you see, about 20 years ago, we developed 4 boreholes, 2 vertical boreholes and 2 inclined boreholes with a depth of 30 meter at Ma Wan Park. You can visit Ma Wan Park. It's a very beautiful park for research. But it's not easy because in Hong Kong, the underground is rock, not soil. The drilling cost is very expensive. So later, we didn't do such project, but we use buildings foundation tile. If we can save the drilling cost, we don't have drilling cost, then it is feasible. If we include drilling cost in Hong Kong, then no payback. It's very, very expensive. So we installed a heat pump system with a unit watt-to-watt heat pump of 4.5 kilowatt for cooling and 4.9 kilowatt for heating. You may say, can we just use the system for cooling in summer or throughout year? I must say it's not good, because if you inject too much energy into the ground, what happens? The temperature is higher and higher because no much water flow inside. Then heat energy is accumulated around that area. I'll show you later. You see, this is a ground coupled heat pump system. How does it work? These are the boreholes. Underground are the boreholes. And then you see, these are the ground boreholes, and then U-tubes, and if you are BSc BEE student, you may understand it. Then this is a same, exact same for traditional air conditioner or refrigerator. Usually for air conditioning system, window air conditioning system or split type air conditioning system, we have a condenser, we have an evaporator, and we have a compressor and an expansion valve. 4 components. Then how does it work? In summer, for example, in summer, we need, you see this one, heat takeout. This is for heating. Let's say in winter, we want to produce hot water for space cooling, and then we have a refrigerant, a kind of refrigerant, a kind of fluid inside to flow in the system, closed system, driven by the compressor. Compressor just like a pump. Compressor. Then the refrigerant passing through the compressor, so the passing through the compressor, the temperature and the pressure are higher. And then the temperature is higher, and then we have a heat exchanger here called condenser. Then we can use the energy to cool it by external cooling system, the heating system, to supply hot water. Then the vapor is condensed into liquid, and then through expansion valve, the pressure is lower, the temperature is lower, and then we have passing through evaporator. Then we need energy. Because we produce energy here, so we need energy input. Then we use energy from underground. So we have another loop, underground loop. We have a pump to take energy from underground to heat this evaporator, and then we have a cycle to produce hot water. Then how about summer? We want to produce cold air or chilled water, and then this becomes an evaporator, and this becomes a condenser. Then we need to reject energy into the ground, and then we get cold. Then this will reverse. We get chilled water. So this is a system. So one problem appears. If we use such a system throughout the year, like PolyU, we have chilled water supply nowadays. Throughout the year, what happens? We have to reject energy continuously to the ground. Then heat accumulates underground, and the temperature is higher and higher, then the COP is lower and lower. We have compared the performance with traditional air-cooled system, and it's not economical. So that's why in Hong Kong, not in Guangdong area, not many such systems are used. Only some trial projects. So in hot weather area, it's not popular. The payback is very long. So this technology is mainly used in, especially in the weather of hot weather in summer, cold weather in cold. Is cold in this area, cold winter, hot summer, like Beijing, Tianjin, even Shanghai. Then gradually to Guangdong, not hot. You can see the problem. This one. The ground coupled heat pump system will experience performance degradation when utilized for cooling load-dominated building. For example, these are the boreholes. Then, gradually, we inject energy into the ground. We use the word inject, not reject. Inject energy into the ground. Gradually, you can see the temperature is higher and higher. We know the efficiency, the COP of heat pump air conditioning system, in fact, is significantly affected by the temperature. So if this temperature is higher, the COP is lower. Then, if we use the system in winter to extract energy from underground to the heat pump system, then this temperature could be cool, lower. Then we can get a balance. But if we continuously inject energy into the ground, like Hong Kong, then no balance. We call it imbalance. So that is a significant problem when we use it in hot weather area like Hong Kong. We are now working on it to solve the problem. The installation of conventional ground coupled heat pump heat system requires high initial cost, especially the drilling cost, and certain amount of ground area. The underground part of the system is called ground heat exchangers, GHE, ground heat exchangers. But, of course, we have advantages. In some areas, high efficiency. Why? Because the ground temperature is lower in summer compared with outside air. It's higher in winter compared with outside air. Like Beijing, for example, in winter, outside air could be negative 9, 8, 10. But inside, in the ground, it's 14 degrees Celsius, much higher, of course. The COP, the efficiency of heat pump is higher. Even in Hong Kong, ideally, the ground temperature 22 degrees Celsius, but the outside air is 35 degrees Celsius in summer, in July and August. Of course, the heat pump system efficiency, or we call it COP, is higher. That's the main reason. High efficiency, why do we call it low operation and maintenance fee? Because we don't use chilled water for cooling. We don't use air-cooled equipment, heat exchangers, and so on. Very reliable, I must say. We just need a pump. And the pipeline, underground pipeline is also cheap. No noise, of course. Do not affect the appearance of buildings. This is especially very good because if you check the rooftop area in PolyU, you will see a lot of equipment. What are they? They are condensers, air-cooled condensers, water tanks, or water-cooled cooling tower. So that, but ground coupled heat pump system, we don't have such equipment. High reliability and long operating life could be used for many years, 20, 50 years. Limitation. Large ground surface area is needed. Remember, we need ground area. But even it can be covered by grass as a park, garden, but we need ground area. High initial cost, especially the drilling cost, very expensive. That's why we are now trying to use piles of foundation piles of buildings, because each building has foundation piles, many in Hong Kong. Then if we can fix the pipeline on the outside or inside of the piles, concrete piles, we don't need drilling cost currently. So that's why we're using foundation piles for ground coupled heat pump system to solve the high initial cost limitation. The last limitation is system degradation for buildings with unbalanced or imbalanced heating and cooling loads. This is a serious problem for continuous cooling in Hong Kong. For example, we inject too much energy into the ground. Then, in that area, the ground area, space, the temperature is higher. Of course, if you stop it, gradually the temperature will be lower and lower, but it takes time. If we have underground water, evacuation, then it is fast. So we must solve the degradation problem or limitation for ground coupled heat pump system. That is one of our research focus in the past. For example, this is one of our research projects. It is called Study on Inclined Ground Heat Exchange Boreholes for reducing occupied ground surface area. You see, we know in Hong Kong we have to inject a lot of energy into the ground. Then we need to drill boreholes. Then if the boreholes are all vertical, exactly vertical, then if we have these boreholes, then the underground area is limited. But if we can drill inclined boreholes, inclined to the outside, then the underground space is much larger. So then we can partially solve the unbalanced problem to inject energy to large space. That's called inclined. You may say the cost may be higher a little because the machine can drill inclined boreholes. Very not difficult, very easy. So we drilled 2 inclined boreholes and 2 vertical boreholes at MAR1 project, for the MAR1 project about 20 years ago, and we started the experiments, and we found that it's very good, very effective to reduce the occupied ground surface area, elevate the thermal interference among adjacent boreholes. This is a cross-section of the inclined boreholes. Then, one of the main contributions to this professional area is the developing an analytical solution of the heat transfer underground surrounding the boreholes. For example, started from vertical boreholes, then we, from Shandong Jiangsu University, we had very good collaboration with the university, and several high-ranking students came from the university for PhD study with me. You see, this is one of the PhD students' project. She developing the simulation model, this analytical simulation model. You know the Green's function, and then to solve the partial differential equation of heat conduction underground. You see, this is a basic case of single inclined borehole. This one, inclined borehole underground. Then we use three-dimensional heat transfer partial differential equation to find the temperature at any position underground, below the surface. Then how to do it? Imagine, you say approximate as inclined line source. The borehole's diameter is very limited, only about 200 millimeter. The borehole, maybe, or 150 millimeter. Then the U-tube diameter is only 3 or 4 millimeter, 40 millimeter. The diameter of the U-tube inside. So, compared with the length of the borehole, 150 or 50 meter, 100 meter, and compared with the large space on the ground. In fact, this diameter is very limited. Then we consider the borehole is a line source, energy source, to transfer energy to the surrounding soil. That's why we call it inclined line source. We simplify. For any analytical solution, we must make a lot of assumptions. This is one of them. You may say the final result may not be correct, not very correct, I must say, but accurate enough for engineering use. Line source with a finite length h underground. Then the heating rate per unit length of the source is a line source. Line source means no diameter is considered. Then the heating rate, we just consider how much energy in joule per meter of the borehole is emitted. Then we say it's constant. That is another assumption. In fact, it's not. Why? Because the ground temperature is not constant. Deeper, maybe lower, or maybe higher, depends on the region, on the area. But here we have to consider the temperature, the source is the heat transfer from the line source. Borehole is constant. I mentioned that for any analytical solution, in fact, we must make some assumptions. Then we can solve the partial differential equation. Another assumption, the third one, the temperature of the ground surface is said to be constant at T0, but it's not. The temperature of the surface, ground surface, in fact, changes every day, throughout the year, because we have solar radiation. Then the last one, very important, a virtual line sink with the same length but a negative heating rate QL, negative QL is set on symmetry to the boundary of the surface, ground surface. Negative Q. In this way, we can use the Green's function and then to solve the partial differential equation. I must say, I don't want to introduce all the details of the simulation model. If you're interested, you can read the paper or papers. But I want to emphasize that analytical solution is more important. If we can find the analytical solution, then it's very easy to publish. Simulation result may not be very accurate, but analytical solution, if correct, analytical solution, then it is accurate, I must say. Of course, we also did validation as well. In the last session, I always said we need validation. We need experimental validation. Then it's easy to publish. You say this is a part of the solution. T, X, Y, Z, top. X, Y, Z is a three-dimensional location on the ground. At any position on the ground, T means temperature. Tau means time. Anytime, any position on the ground, we can find the temperature through this analytical solution result. Then the last one, the temperature rise on the borehole wall in the ground heat exchanger can also be found from the principle called superposition. You say superimposition. That means we have to consider all the responses from all other boreholes, not just this one borehole itself. All the boreholes heat transfer will add the response. So you can see the arbitrary heating or cooling load, sequential temporal superimposition to determine the final temperature. We add all these responses together. Then I'll show you the result. You see, if we use inclined boreholes, you see the angle between the vertical direction and the inclined borehole is alpha, let's say 0, that's vertical borehole. Alpha 10 is 10, that's the angle is 10. Inclination angle 10, 20. You can see the temperature on the left, the vertical coordinate. The temperature is lower, much lower, when the angle is 20. angle is 10. When angle is 0, that's vertical borehole, the temperature could be 70, but 10 degrees Celsius, 10 degree borehole, vertical borehole, inclined borehole, the temperature is 55. 20 degree, the temperature is less than 50. It means if we continuously inject energy into the ground in summer in Hong Kong, it's better to use inclined boreholes. These students published a lot of journal papers that time. You see the last sentence? The thermal influence of the inclined boreholes was significantly reduced owing to its larger borehole space under the ground. So vertical boreholes can solve partial problems, not all the problems, I must say. And we did experiment from the test rig at the Ma Wan Park. The test rig is still there. There are 4 boreholes. You see, the relative error was within 12%. That's very good for such engineering project. Usually we check the existing water temperature from heat pump. Existing water temperature means entering temperature to the borehole. Another one is entering water temperature to heat pump means exiting water from the boreholes. Then we compare our simulation result from the analytical solution with the experimental result. Then the error is only 3. The maximum temperature difference is less than 3 degrees Celsius. Then this is interesting. You can see another study. We use numerical finite element method. I believe, especially from civil engineering department, some of you are using finite element method, FEM, to solve some heat transfer problems. Very useful tool. Then we divide the borehole domain with many mesh. We have to set up the meshed model first. You can see at the center is a borehole. But I must say, the borehole now is not a line source. We have to consider the inside of the borehole. You see, this is a borehole. We must consider the heat transfer from the water in the pipeline to the surrounding in the borehole. Not inside is not water surrounding the pipeline. The pipeline is only 3 or 4 centimeter diameter. Then surrounding the pipeline, it is we called you see, we called ground, backfield. As shown. You see, if this is the ground, and then we drill boreholes, then this is the ground, soil. Then we put one U-tube pipeline. One U-tube pipeline. Then inside water flow, of course, outside pump. Then how about this space? We fill groove. That's a kind of concrete with high thermal conductivity. That's what we call growth backfill. Otherwise, the two pipelines may be touched. We must separate the two pipelines, the U2 pipeline. At the same time, we need heat transfer from surrounding to the pipeline water, so that we need high thermal conductivity growth backfilled in the borehole. So that's why in the middle is a growth backfill in the region of borehole. That's the pipe wall. Then especially the outer region is the soil surrounding. Then to use finite element method, we need to divide into, you see, this is a mesh model, this is a borehole, this is a borehole enlarged, and then surrounding it, we need more. Then we want to calculate the temperature at any time, at any location. Then it's not easy to use the analytical solution. But it's possible to use finite element method, the numerical simulation. And we develop the governing equation for element. Everybody, I think I think most of you know this heat transfer partial differential equation. On the left is the source, on the right the temperature distribution. And the heat transfer for the element, for each element. Nowadays we have a computer, then we can solve the partial differential equation through numerical simulation. And then I want to show you the result. You can see the temperature distribution. At the beginning, let's say for a few days, the temperature surrounding this area will not be affected, only this area. Then we enlarge this area into this, and we found that this temperature higher and gradually lower. You can imagine, if this temperature, for example, in Hong Kong, in summer, is much higher, we inject energy continuously on the ground. If this temperature, originally, if no injection, the temperature is 22. Then steady state throughout the year, no change in Hong Kong. But if we inject energy into the ground, let's say 20 hours a day, then the temperature will be higher surrounding the borehole. If the temperature is higher, 30 degrees Celsius, then compared with outside air, then the COP will be lower, much lower. That's why, that's the main reason in Hong Kong for not using ground coupled heat pump system. We have only one commercial project where, in the wetland park, only one. And then from our research project, we developed two projects, one in Ma Wan Park, another one near Ma An Shan. We did some research. But now, some companies want to do more because they think that we have solved some problem. You see, the ground initial temperature, the blue one, let's say in Hong Kong, 22. And gradually, the temperature is higher and higher surrounding the boreholes. So with the finite element method, we can find the temperature at any position, anytime. So we found the temperature contours of the whole region after about 1 month. Then we can continue the calculation and then find the temperature distribution after 1 year or even 10 years, 20 years, and then predict the future COP of the system. So then we studied another study that's called hybrid system. We want to solve the imbalance problem, energy imbalance problem, because we inject too much energy into the ground, then we think that we may solve the problem partially. For example, if we can use hybrid system, hybrid ground coupled heat pump system for areas with unbalanced cooling and heating load, as typically in Hong Kong, Guangdong area, because we nearly don't have winter. We don't need heating. Then, first, we did some research for cooling low dominant building. We developed the hybrid ground coupled heat pump system with desuperheater, with cooling tower, with nocturnal cooling radiator by the three means. Then let's see how to do it. We also did some research in ground coupled heat pump system for heating low dominant buildings like Harbin. Nearly no cooling necessary in summer, only heating. Then if we use ground coupled heat pump system, we only extract energy from the ground. But we don't need to extract energy from the ground all the year, because in summer we don't need it. They don't need heating, but they don't need cooling as well. Then the temperature on the ground gradually recover. So we did some research in this area. For example, the cooling load dominant building, can we use the system to produce hot water at the same time? We don't want to solve the problem for all the buildings, all kind of buildings. But for example, in hospitals, hotels, we need hot water. Residential buildings, we need hot water nearly every day throughout the year for washing, for bath, taking shower. Then, for such buildings, we can produce hot water, you see, at the same time, and then hot water supply buildings, and the domestic hot water supply. Sorry, this is a cooling. This is a domestic hot water supply. At the same time. Why? Because after the compressor, the temperature is very high. Then, if we inject energy, this energy into the ground, then too much energy inside. Then we can cool this refrigerant by external hot water supply system, reduce the temperature, and get some energy first. Then we inject the remaining to the ground. So in this way, we can solve the problem partially. It depends how much hot water we need. So this is called hybrid system with desuperheater. So number 1 to 2 is desuperheater. Then it means we cool the refrigerant through heat exchanger after the compressor. Then we can reduce the load inject into the ground. If we check the pH diagram on the right, I think most of you do not understand it. Then it's easy to understand it, the principle. But it just knows that if we can produce chilled water and hot water at the same time to supply hot water for taking shower, for washing in kitchen, and hotel, and hospitals, then we can increase the COP of the system. So this is called hybrid ground coupled heat pump system with de-superheater. Of course, this is used in Hong Kong, in hot weather area throughout the year. Then we did some simulation by of the system first, and then underground by finite element method. You can see the COP. There are three curves. The COP means coefficient of performance, then also efficiency of the chiller, air conditioner. We don't call it efficiency because it's greater than 1. You see, there are three curves. The blue one is a COP with domestic hot water supply. The pink one, heating with domestic hot water mode. Then the green one, cooling only mode. You see? If we have hot water supply, even for heating and for cooling, the COP much higher. Especially the blue one, the COP, you see, it's about more than 3 or 4, sometimes even 4.5. But if no hot water supply is less than 3, if the COP is less than 3, we say it's not efficient. Because you can use compression refrigeration system. Then other parameters. You can see the COP on the right bottom one, the power consumption, the COP of the system. So less COP means more power consumption. Another solution to solve the unbalanced problem, energy injection problem. We can use a cooling tower. Traditionally, for most of the air conditioning system in China, we use cooling tower. In Hong Kong, we don't use too many cooling towers, but nowadays we use some because cooling tower need fresh water for evaporation, and then we need to consume some fresh water into the air. Most of fresh water in Hong Kong is imported. We buy fresh water from Dongjiang River of Guangdong. You know how much now? About 7 Hong Kong dollar per cubic meter. Very expensive, correct. Then the government restrict the use of fresh water for cooling tower. But now relaxed because we have fixed amount of water purchased from Guangdong. It means we sign the contract, then we pump water from Dongjiang River to Hong Kong. Even though we have more rain on that year, then we still have to buy the amount of fresh water. Then it means we may have surplus of fresh water. Then we can use such surplus fresh water for cooling tower. Because you see, cooling tower, the COP is much higher. Then, can we use cooling tower for this coupled heat pump system in a short time period? For example, in July and August, only afternoon or from noon to afternoon, then when we have peak cooling load. It means we want to combine our ground boreholes and the cooling tower. We only use the cooling tower to reject some energy to the air by evaporation. Some time, limited time. Most of the time in the year we don't use it. In this way, we can solve the problem partially. Then we need more equipment. A cooling tower and a heat exchanger. There's a heat exchanger, plate heat exchanger. You see more heat exchangers. At the same time, we still produce hot water. DHW, that's a hot water. Then we did some comparison of energy consumption between the hybrid system and the ground coupled system for office building with unbalanced ratio 1.59. Too much energy injection to the ground. You can see the hybrid system, the control strategy number 3, number 2, number 1, number 3 is the best. For various costs, drilling cost, maintenance cost, and CC initial cost, the total cost is less. There's an optimal control strategy, is a temperature difference control strategy. The optimal hybrid ground coupled heat pump system can reduce 35% of the initial cost and 20.79% operation cost in the first year. And we also did experiments to compare the performance with and without cooling tower. We did these experiments. I'll show you the details later. In Handan, that's a Hebei Engineering University. They drilled several 100-meter depth boreholes. I sent one of my PhD students over there to do experiments. You see, hybrid system, then ground coupled heat pump system, and initial temperature of ground, the green one. That's a borehole wall temperature. Let's say the right top figure, COP. We are interested in the COP, the coefficient of performance of the pump, heat pump. You can see the hybrid system with cooling tower, the COP could be more than 5. That's much better than the red one. And you can compare the hybrid system with cooling tower and the ground coupled heat pump system only, without cooling tower. You can see the initial cost and 10 years operation cost is much less. The hybrid system much less. It means we can inject some energy from the cooling tower to the air in some limited time period, which can solve some unbalanced problem. And then you can see the test result, experimental results. The black one, ground coupled heat pump system, the COP is much higher. And the red one, ASHP, that's air source heat pump. That's the most popular air conditioning system in Hong Kong. Most of the air conditioning system in Hong Kong we use air source. Especially our home air conditioner, like split type air conditioner, window window type air conditioner or air source heat pump. It means we inject energy to the air. We use the air to cool the condenser. Large system in PolyU, we also use air source heat pumps. Air source heating cooling system. You can call it heat pump, but it's for cooling. Air source. That's why most of the roof area in PolyU, the equipment in fact is condenser, air condenser. You can see the right bottom figure, power consumption of the heat pump. Red one, you can see traditional ground coupled heat pump system. And then black one, hybrid ground coupled system with cooling tower or undamaged hot water supply. You see the power consumption is nearly half or 1/3 of the power consumption without these two methods: damaged hot water supply and the cooling tower. Then we use another method to solve this unbalanced problem. This method called nocturnal cooling radiator. Some of you, especially BEE students, you are familiar with this term, nocturnal cooling radiator. That means we add heat exchanger on roof, then with water flow or other liquid flow inside, especially in evening or nighttime, because the sky temperature is very cold. In theory, clear sky, for example, no cloud, then the temperature is absolute zero. So that the heat transfer between the panel and the sky take place. Because the large temperature difference by radiation, we can cool water in the panel. This is called nocturnal cooling radiator, NCR. Some research, also from, for example, from Professor Lee of BE's department, also thinks that if we can put some coating on it, we can even use it during daytime, under sunshine. You may say under sunshine the temperature could be higher, but no, because of the coating, high reflectivity or high emissivity coating, then we still can have more energy transfer by radiation from the panel to the outside, to the sky, even under sunshine, but limited, I must say limited. So we can use this technology to cool the condenser. Then we can reduce the amount of energy inject into the ground by the ground heat exchanger. This is also very useful, very effective. This is the structure of nocturnal cooling radiator. That's a heat exchange between the fluid in the condenser and the outside air or sky, in sky. That's easy to understand. If no air conditioning system, people tend to stay outside at night time, evening. Why? Because cold. Not just the air temperature cold, because the long wave radiation from our body to the sky, especially without cloud. So that's why people would like to stay outside, on roof especially, when we don't have air conditioner at that time. So this is called nocturnal cooling radiator, also very effective. There are advantages. We can install the radiator on the roof of building horizontally. It does not affect the building appearance. No rotating parts, no noise, long-time performance, nearly no maintenance, easy to operate, inexpensive model. You can see we developed a simulation model. These students published a number of papers in this area because original and analytical solution. And you can see the research found that the COP could be much higher. This cooling capacity of radiator depends on the flow rate and temperature, of course. I think we need to, yeah, the COP. The total energy, total cost, you see, it depends on depth of the borehole as well. I think we need to compare this one. Yeah, the hybrid system and compared with the ground coupled heat pump system without the previous three methods, then you can see the total cost is much less. I save 10.22% of the total cost over 10 years. Okay, let's take a break, 10 minutes break, and then we'll introduce other